In Module 11, Section 7, we will discuss complex numbers. Previously, when we encountered square roots of negative numbers in solving equations, we would say we have no real solution or the solution is not a real number. And while that's still true, we will now introduce a new set of numbers that will take care of this issue. These numbers are called imaginary numbers, which includes the imaginary unit I. The imaginary unit, written I, is the number whose square is negative 1. That is to say that I squared equals negative 1. So then the square root of each side would give us I equals the square root of negative 1. Let's try to rewrite a few radicals using I notation. Before, we would write these as not a real number because we have a negative sign underneath the square root. Instead, we are now going to rewrite this, pulling the negative to the outside and rewriting it as an I. So that becomes I square root 25. We know the square root of 25 is 5. So this becomes 5I. In the next example, again, anytime we have a negative underneath the square root, we rewrite that as I times the positive number that was left under the square root. So I square root 32. Because 32 is not a perfect square, we need to write its prime factorization. So 32 equals 2 times 2 times 2 times 2 times 2. Remember, because the index is 2, we need two identical factors to form a group. So we have two 2's that forms one group, another set of 2's that forms a second group. So we have two groups of 2's. 2 times 2 is 4. We can rewrite this as 4I square root of, we have one 2 that remains underneath the square root. And in the last example, we have negative or the negative square root of negative 121. Now, when we pull the negative from the inside and rewrite it as I, it does not change the sign outside of the square root. So we have negative I square root of 121. 121 is a perfect square, and its square root is 11. So this becomes negative 11I. We can also multiply or divide when we have a negative underneath the square root. Here we have the square root of negative 3 times the square root of negative 5. If we use the product rule, we write one square root, and each radicand underneath multiplied together. Negative 3 times negative 5 is positive 15. So the answer is the square root of positive 15. In the second example, if we use the quotient rule, we can rewrite this as the square root of negative 125 over 5. If we divide underneath the square root, we have the square root of negative 25, and as we saw earlier, that would become 5I. Now let's talk about complex numbers. A complex number is a number that can be written in the form a plus bi, where a and b are real numbers. A is the real number, and bi would be an imaginary number. If b is 0, then a plus bi is a real number because the imaginary part doesn't exist. If a is 0, a plus bi is an imaginary number because the real part does not exist. Now let's talk about adding and subtracting complex numbers. You see the rules shown below. It's going to be more or less the same rules that would apply to adding or subtracting polynomials. We combine the real parts, combine the complex parts, and make sure to distribute your negative sign if we are subtracting. Let's try a few examples. Here we have two complex numbers, 4 plus 6i and 3 minus 2i, and we want to add. First, we drop the parentheses and just write our expressions. So 4 plus 6i plus 3 minus 2i. Now we combine real parts. 4 and 3 gives us 7. Combine imaginary parts. 6i minus 2i is 4i. Don't write 4i squared. We treat the I like a variable. In the next example, we have 8 plus 2i minus 4i. So we can rewrite this as 8 plus 2i minus 4i without any parentheses. We only have one real part, and that's 8. So 8, we have two imaginary parts. 2i minus 4i is a negative 2i. To multiply complex numbers, we multiply as though they were binomials. Then we use the relationship I squared equals negative 1 to simplify. Let's try to multiply 8i times 7i. So we multiply the coefficients. 8 times 7 is 56. I times I is I squared. Remember that I squared is the same as negative 1. So we replace I squared with negative 1, and the answer is negative 56. Let's try another example. 5i times 4 minus 7i. So we distribute the 5i into the parentheses. 5i times 4 is 20i. minus 5i times 7i is 35i squared. Remember, anytime we see I squared, we replace it with a negative 1, and this becomes 20i plus 35. Here we have an example where we are multiplying two complex numbers where each part is present. So we're going to FOIL, first, outer, inner, and last. Our first product, 6 times 7 is 42. Our outer product, 6 times 4i is 24i. Our inner product, negative 3i times 7 is minus 21i. And the last product, negative 3i times 4i is minus 12i squared. Now, just like we've done previously, we need to change the I squared to a negative 1. Everything else will stay the same. So 42 plus 24i minus 21i minus 12 times negative 1. That becomes 42 plus 24i minus 21i plus 12. Now we combine our real parts together, and that gives us 54. Combine the imaginary parts together, and that gives us a 3i. So 54 plus 3i. In the previous chapter, when we tried to rationalize the denominator of a rational expression containing radicals, we use the conjugate of the denominator. Similarly, when we divide complex numbers, we will need to use the complex conjugate of the number we are dividing by. The complex numbers a plus bi and a minus bi are called complex conjugates. So similarly to the conjugates we've used before, the first terms stay the same. Here the imaginary numbers change signs. And when we multiply a number by its conjugate, we only need to look at the first FOIL arrow and the last FOIL arrow. A times a is a squared. Bi times negative bi is negative b squared I squared. But remember, this I squared always changes our sign. And that's why it becomes a positive b squared. Let's try a couple of examples. Here we have 6 plus 2i, all divided by 4 minus 3i. So we multiply top and bottom by the complex conjugate of the denominator, which is 4 plus 3i. In the numerator, we will need to FOIL, first, outer, inner, and last. Doing so gives us 6 times 4 is 24, 6 times 3i is 18i, 2i times 4 is 8i, and 2i times 3i is 6i squared. In the denominator, because we have conjugates, we can just look at the first FOIL arrow and the last FOIL arrow. 4 times 4 is 16. 3i times negative 3i is minus 9i squared. Let's change our I squareds to negative 1, or we can just drop the I squared and change the sign of that term. That will give us 24 plus 18i plus 8i minus 6 all over 16 plus 9. At this point, we can combine like terms. 24 minus 6 is 18. 18i plus 8i would be a 26i. All over 16 plus 9 is 25. We could leave it in this form. However, we want to write it as a complex number, a plus bi, where we have one real part and one imaginary part. So we're going to split this fraction into two fractions. That would become 18 over 25 plus 26 over 25i. Let's try another example, 5 over 6i. Now, because our denominator only contains the imaginary part, remember, when we multiply by the complex conjugate, the only thing that changed was the sign of the denominator. So let's multiply by negative 6i. When we do so, in the numerator, 5 times negative 6i is negative 30i, over 6i times negative 6i is negative 36i squared. Remember, the I squared changes the sign of the term, so this becomes negative 30i over a positive 36, and now we can reduce. 30 and 36 have a common factor of 6. If we divide both by 6, we're left with negative 5i over 6.